In this third lesson of chapter 3 of the course of basic geometry are presented the definitions and properties of the various centers of triangles and the relationships between the hypotenuse and the median. The topics presented are definition of triangle centers and the relationships between hypotenuse and the median. In this first slide of this third class of chapter 3 of this course of basic geometry, the figure 3.16 presents the concept of orthocenter of a triangle. Initially, it presents the definition of a height of a triangle, defined as the line that has the origin at the vertex and that is perpendicular to the opposite side of the triangle, or perpendicular to a segment of the extension of the straight line comprising the opposite side. The side where the perpendicular originates is called the base of the height, and the point where the perpendicular originates is called the foot of the height. Thus, the triangle has a height corresponding to each side. The point where the three line segments called the heights meet is called the orthocenter of the triangle and is represented by the point H. In an acute triangle, the orthocenter is inside the triangle. In a right triangle, the orthocenter coincides with the vertex of the right angle. In an obtuse triangle, the orthocenter is outside the triangle. In this second slide of this third class of chapter 3 of this course of basic geometry, it presents a figure 3.17, which introduces the concept of circumcenter of a triangle. Initially, it shows the definition of the bisector of a line, that is, the side of a triangle is perpendicular to the side line of the triangle drawn at the midpoint of the side. The triangle has three bisectors of the side line segments, each one associated with one side of the triangle. The meeting point of the three bisectors is called the circumcenter point, represented by the point M. The circumcenter is also the center of the outer circumference, circumscribed to the triangle, passing through the three vertices. In an acute angle triangle, the circumcenter is located inside of the triangle. In a right triangle, the circumcenter is located at the center point of the hypotenuse. In an obtuse triangle, the circumcenter is located outside of the triangle. In this third slide of this third class of chapter 3 of this course of basic geometry, it is presented figure 3.18, which introduces the concept of centroid, or center of gravity of a triangle. Initially, the definition of a median of a triangle is presented as a line segment joining a vertex of the triangles to the midpoint of the opposite side. The intersection of the three medians is called the centroid, or center of gravity of the triangle, shown in the drawing by point G. In this slide and in the following one, the relation between the segments of a line divided by centroid is shown. The line segment that originates from a vertex to the centroid is twice the size of the line segment that originates in the centroid point and intersects the middle of the opposite side. To prove this statement, we use the triangle ABC in the figure 3.19. In this triangle are drawn the three medians, which are intersected at the point G. Continue with the proof process. The median that originates at the vertex B is prolonged. As it is drawn a line segment that originates at the vertex A parallel to the median that originates at the vertex C. First, the median originates from the vertex B is extended, and it is drawn parallel to the median originating at the vertex C, passing through the point A, that is the line segment AH. The intersection of a median and station that originates at the vertex B with the line parallel to the median of a vertex C that originates at the vertex A, results in the point H. Continuing with the proof process, it is verified that the triangle CEG and the AHE are equal, because in the vertex E, the internal angles of both are opposite and therefore are equal. On the other hand, the line segments AE and EC are equal by definition of the median that originates in the vertex B. Also, the ACD and HAE angles are the same because the straight line segments AH and CD are parallel, and the AC line segment is common to the two triangles. Continuing with the proof on this next slide, figure 3.19 is presented again, and you verify that the triangles AEH and CEG are the same because they have one equal side and two equal angles at the ends of the side that has the same dimension. Therefore, the AGE and the EG line segments have the same dimensions, they are equal. But the BDG and BAH triangles are similar because the line segments AH and DG are parallel, and the GBD angle is the same on the vertex B. But the straight line segment AD and DB are equal by the definition of median. So the line segment BH is divided in two parts equals by the G point due to the similarity of triangles and the fact that the side AB of the triangle has twice the size of the BD side. Finally, we conclude that the line segment BG and GH have the same dimension. But the straight line segments HE and EG are equal. Then the line segment EG has half the dimension of the line segment BG. In this slide, you analyze the relationships between the dimensions of the hypotenuse and the dimension of the median in a right triangle. In a right triangle, the median that originates at the vertex of the right internal angle and finds the median point of the hypotenuse has the dimension equal to the half the dimension of the hypotenuse. To carry out this demonstration, the triangle ABC and the median BD are shown in figure 3.20. At the vertex A, it is raised a perpendicular, and the median is prolonged until it finds the right angle perpendicular AE, created in triangle ABE. BDC and ADE triangles are congruent because they have two equal angles, opposite angle at the point D, and equal angles EAD and DCB, and a common straight line AC, dividing the two equal line segments AD and DC. In this new and last slide of this class, it's shown that the ABE and ABC triangles are also congruent. That is, they are the equal because the AB side is common and the AE and BC perpendicular line segments have the same dimensions. Then the line segments AC and BE are equal. Because of the symmetrical position of the triangles ACB and ABE, the point D also divides the segment BE into two equal segments, BD and DE. Next, the line segment AC, that is the hypotenuse of the triangle ABC, is composed of the sum of the segment AD and DC having equal dimensions. On the other hand, the segment BD has the same dimension of segment AD. Hence, the median that originates at the vertex B is half the size of the hypotenuse.